Welcome to ScienceCover.com. In this session, we look at specific latent heat. We'll focus on what we mean by specific latent heat, how to calculate the specific latent heat, and then how to rearrange the equation. First, pause the video and complete the Do Now task. Let's check our answers. What is the equation that relates mass, volume, and density? Density is the mass divided by the volume. What are the units of density? Kilograms per meter cubed or kilograms per centimeter cubed? What are the three states of matter? Solid, liquid, and gas. What word would you use to describe a change from a liquid to a gas? Is evaporating. Gas to liquid is condensing. Liquid to solid is freezing. Solid to gas is subliming. What is the internal energy? It's the sum of all the particles' kinetic energies and potential energies. What is the kinetic energy of the particles? It's the energy that the particles have stored in their movement or motion. What is the potential energy of the particles? It's the energy that a particle has due to its position under interaction with other particles. Why does the temperature stay constant during a change of state, even if heat is being added or removed? The energy is being used to change the potential energy of the substance. This creates or breaks bonds. Energy is not used to alter the kinetic energy of the particles, so the temperature remains constant. Let's look at what we mean by the specific latent heat. To turn a solid into a liquid, we have to add energy, but how much? This depends on two things. Firstly, the amount of substance. If we have more mass, then we need to add more energy to turn it from a solid into a liquid. But the other thing it depends on is what the substance is made from. Now this is in science what we refer to as the specific latent heat. It's a value that's assigned to the material itself that tells us how easy or difficult it is to turn that material from a solid into a liquid. Now since we need to assign a number, we have to calculate that number. And so we can do that by using the equation energy is mass times by specific latent heat. If we rearrange this to get the specific latent heat, then what we need to do is to work out how much energy it takes to change something from solid into a liquid, and then divide it by the mass that that material has. And this will give us a value for the material that we can then compare to other materials. We can define the latent heat as the amount of energy required to turn 1 kilogram of material into a different state. And this occurs at 2 points. Firstly, when a substance is melting, so we call this one the latent heat of fusion. And the other time we see a change of state is when we're changing from a liquid into a gas, so we call this one the latent heat of vaporization. Well, for a material, the latent heat of fusion and latent heat of vaporization will not have the same number. So if we want to define the specific latent heat, we can say that the specific latent heat is the amount of energy required to turn 1 kilogram of a material from one state into another. But if we want to be more specific and talk about the latent heat of fusion, then we need to say that it's the amount of energy required to turn 1 kilogram of a substance from a solid into a liquid. Now, the latent heat of vaporization is the amount of energy required to turn 1 kilogram of a substance from a liquid into a gas. So pause the video and complete task 1. Let's check our answers to task 1. Define the latent heat of fusion. The amount of energy required to turn 1 kilogram of solid into a liquid. Define the latent heat of vaporization. The amount of energy required to change 1 kilogram of a liquid into a gas. Complete the equation to calculate the energy used to change state. Energy is mass times by specific latent heat. Mark on the graph where the substance is changing from a solid to a liquid with an X, and mark on the graph where it's changing from a liquid to a gas with a Y. Well, the X should have been placed on the constant temperature at 0, and the Y should have been placed at the constant temperature at 100 degrees Celsius. Now let's focus on how we can calculate the specific latent heat. We learned earlier on that the amount of energy required to change a substance from one state into another depends on both the mass and the specific latent heat of the material. So to calculate the energy in joules that is required to cause that change of state, we just need to take the mass in kilograms and multiply it by the specific latent heat. Let's look at some examples. A man boils 0.2 kilograms of water at 100 degrees Celsius from water into steam. Calculate the energy used if the specific latent heat of vaporization of the water is 2,300,000 joules per kilogram. Well, first we write the equation. So we know that the energy is the mass times by the specific latent heat. And the mass we've been given is 0.2 kilograms. The specific latent heat of water is 2,300,000. So if we multiply these two together, it tells us that the energy required to cause this change of state is 460,000 joules. A Martian turns 3 kilograms of ice into water. How much energy was used? The specific latent heat of fusion of ice is 330,000 joules per kilogram. So again, we know that the energy is the mass times by the specific latent heat. This time we've got a mass of 3 kilograms. And the specific latent heat is 330,000 joules per kilogram. So if we multiply these two together, we get 990,000 joules. Now pause the video and attempt task 2. Let's check our answers. How much energy is needed to turn 2 kilograms of water into steam? Specific latent heat of vaporization of water is 2,300,000 joules per kilogram. So to work this out, we need to do the energy as the mass times by the specific latent heat. So that's 2 times 2,300,000, which gives you 4,600,000 joules. How much energy is needed to turn 600 grams of solid mercury into liquid? The specific latent heat of fusion is 11,000 joules per kilogram. So the energy is the mass times by the latent heat. So it's 0.6 times by 11,000, which gives us 6,600 joules. How much energy is needed to turn 400 grams of liquid ethanol into a gas at 78 degrees Celsius? Specific latent heat of vaporization of ethanol is 838,000. So the energy is the mass times by the latent heat, which is 0.4 multiplied by 838,000, which is 335,200. How much heat energy is lost when 500 grams of steam condenses at 100 degrees Celsius to become a liquid? It take the specific latent heat of vaporization of water to be 2,300,000 joules per kilogram. So the energy is the mass times by the latent heat, and that's 0.5 times by 2,300,000, which is 1,150,000 joules. Now let's look at how we can rearrange the equation. So we can place the specific heat capacity, energy and mass into an equation triangle. We'll use Q for the energy, M for the mass, and L to represent the specific latent heat. If I want to know the amount of energy needed, I can cover up Q, and it tells me that it's M multiplied by L. So this is the mass times by the latent heat. However, if I want to find out the mass, I can cover up the mass, and it tells me that it's Q divided by L. If I want to find the latent heat, then I cover up L, and it tells me it's Q divided by M. Let's look at some examples. A girl heats 400 grams of oil from a liquid into a gas. This uses 400,000 joules of energy. What is the specific latent heat of vaporization? Well, the specific latent heat is the energy divided by the mass. Now, the energy is 400,000 joules. But the mass, we can't use 400 grams, we have to convert this to kilograms. So it becomes 0.4 kilograms. 400,000 divided by 0.4 gives us 1 million joules. A chocolate bar absorbs 150,000 joules of energy and turns from solid chocolate into liquid. If the chocolate bar had a specific latent heat of 500,000 joules per kilogram, what is its mass? So the mass is the energy divided by the specific latent heat. So this is 150,000 joules divided by 500,000 joules per kilogram, which gives us a mass of 0.3 kilograms. Now pause the video and attempt task 3. Let's check our answers to task 3. Calculate the specific latent heat of fusion if 183,600 joules is supplied to turn 3.4 kilograms of sulfur into a liquid. So the latent heat of fusion is the energy divided by the mass, which is 183,000 divided by 3.4, which is 54,000. Calculate the specific latent heat of fusion at 28,000 joules is supplied to turn 2 kilograms of solid oxygen into a liquid. So the latent heat of fusion is the energy divided by the mass. So this is 28,000 divided by 2, which is 14,000 joules per kilogram. Question 3. 398 joules of energy is needed to turn 500 grams of liquid nitrogen into a gas. Calculate the specific latent heat of vaporization. So the latent heat of vaporization is the energy divided by the mass, which is 398 divided by 0.5, which gives us 796 joules per kilogram. Question 4. Calculate the specific latent heat of fusion if A, 28,000 joules is supplied to 2 kilograms of solid oxygen into a liquid. So the latent heat of fusion is the energy divided by the mass. So this is 28,000 divided by 2 is 14,000 joules per kilogram. In part B, we've got 183,600 joules being supplied to just 3.4 kilograms. So the latent heat of fusion is the energy divided by the mass. It's 183,600 divided by 3.4, which gives us 54,000. Part C, we've got 6,600 joules, and we've got 600 grams of solid mercury changed into a liquid. Now we can't use 600 grams, we've got to change it to kilograms, so it'll become 0.6 as a mass. And so if we divide 6,600 divided by 0.6, it gives you 11,000 joules per kilogram. For part D, you got 67,000 joules, and we're supplying that to 200 grams of ice, changing it into a liquid. So 200 grams will become 0.2 kilograms. So the latent heat diffusion is the energy divided by the mass, is 67,000 divided by 0.2, which gives us 335,000 joules per kilogram. For question 5, we've got to calculate the specific latent heat of vaporization. So part A, we've got 335,200 joules, and we're changing 400 grams of liquid ethanol to gas. So 400 grams will become 0.4 kilograms. So we're doing 335,200 divided by 0.4. This is 838,000 joules per kilogram. Part B, we got 987,800 joules supplied to 2.2 kilograms. So the energy divided by the mass is 987,800 divided by 2.2, which gives me 449,000 joules per kilogram. For part C, we got 53.25 kilojoules, so that's 53,250 joules, and we're supplying that to 250 grams, that's 0.25 kilograms. So if you divide one by the other, you get 213,000 joules per kilogram. For part D, I need to do the energy divided by the mass, so that's 7,620 joules divided by 0.03 kilograms. That'll give me 254,000 joules per kilogram.